Okay, so if you want to see how I got these answers to the math questions, I'm going to go through them. So what was slide 11? Slide 11, if I remember correctly, was this. So you were trying to figure out what is this number? What is this value on the x-axis? Or on the y-axis. And it's hard because if this is the scale and it's a linear scale, all these numbers are smushed together. And that's okay for a lot of things, but for bacterial growth, this just isn't what we want. So if you really wanted to get this number, you could, but it just doesn't matter. I was just trying to show you that it is impossible to get this number. I guess you could look at this one and estimate it, divide it by 2, divide this by 2, divide that by 2, and go backwards, and that's how you could get there. But remember, there are things like lag phase where the cells are figuring out how to grow and they wouldn't be doubling during that time. So you can't know, is this really 2 times what this is? Was it doubling or was it just going up a little bit? You can't know that unless you use something like this. Okay, so the answer to that one doesn't matter, but it was 8 times 10 to the third power. Slide 14 is this one. So let's see. Which of these is closest to 6 times 10 to the fourth cells per milliliter? Okay, so this says population cells per milliliter. So we're just trying to figure out what point on this is closest to 6 times 10 to the fourth power, and then which of these dots is close to that. So how do we find 6 times 10 to the fourth? Well, remember, each of these lines is a different value. The big lines are powers of 10, and then the small lines are divisions within that. And the way it works is, if this is 1 times 10 to the third power, it's also 1,000. This is 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. And then we get to this one, this big line, 10,000. That's 1 times 10 to the fourth power. Now, each of these lines is going to be another addition of 10,000. So it's going to be 10,000, 20,000, 30,000, 40,000, 50,000. And so where along that is 6 times 10 to the fourth? Well, this is 1 times 10 to the fourth, 2, 3, 4, 5, 6. So if we go over here, B is close to 6 times 10 to the fourth power. That's all it is. That's all you do. But I put this in here because you do have to work through that process of understanding, what does it mean if I go from this line to this line? Am I going up by 10 to the third? Am I multiplying by 10? What am I doing? So practice that. Okay, and then this one, slide 20, is the one about the water bottle and the crystal clear water. So remember, if we go back to slide 20, you can hide something like 10 to the 6th cells in 1 milliliter of water, and it's invisible. So that's not enough cells to scatter the light in a detectable way. They're just too small and too spread out. If you see something as cloudy as the bottle I showed you, that would be more like 10 to the 8th or 10 to the 9th cells per milliliter. So like 1 billion cells per milliliter. So 100 or 1,000 times more cells than this. So if we have a water bottle that holds 750 milliliters, and we know you can hide 10 to the 6th cells per milliliter, how many could be hiding in your water bottle? Well, let's see. Let's get a new drawing. I do this in the most explicit way I can. I write out all the units and I make sure they all cancel. And I do it like one step at a time. There are other ways to do it, but this is how I did it. This is how I got through engineering school and stuff, and it has served me well. So I would start thinking about units. The units I want are cells. That's our target, cells. The two numbers we have are 750 milliliters and 1 times 10 to the 6th cells per milliliter. So they are already in a form we're going to like. If we multiply these numbers together, this 750 is on top. So divide by 1 doesn't change it. So we think of this as on top. So if we multiply these together, the units are going to cancel and we'll be left with cells. So how do we do this and do all the scientific notation? 750, in this case we just multiply by times 1 times 10 to the 6th. What I'm going to do is change this into scientific notation, and then I'm going to add all the zeros. So let's see. So this is 750. How do we figure out what that is in scientific notation? Well, it's the same as 750.0. And one way we could look at this is this bigger than 1? If it's bigger than 1, it's going to be a positive power of 10. If it's bigger than 10, it's going to be more than 10 to the first power. If it's bigger than 100, it's going to be more than 10 to the second power. And it is bigger than 100. Is it bigger than 1,000? 1,000 is 10 to the third power. So let me write that out. So this is an important thing to remember. It's 10 to the negative 1 equals 0.1. 10 to the 0 is 1. 10 to the plus 1 is 10. 10 to the 2, 100. 10 to the third power equals 1,000. So this is between 10 to the second power and 10 to the third power. So there's some number we can multiply times this to get this number. So I'm going to use the shortcut, which is I'm just going to move this decimal point to here, because in scientific notation we have one number, one digit, and then all the other digits are behind a decimal point. So I know I'm going to move it twice, or I can count 1, 2. So then the question is, do I go up? Do I go down? What do I do? Well, remember, this is a positive power of 2. It's between 10 to the second power and 10 to the third power, so I know I'm going away from 0, so I'm going up. So I count 2. So it is 7.50 times 10 to the second power. This is 100. 7.5 times 100 is 750. I'm not a math teacher, but you know what you might do if this really didn't work for you is Google Khan Academy scientific notation. There's probably some very clever person who explains it very clearly. And math teachers kind of remember the steps that you need, and I remember the shortcuts that you don't need to know. So that's how I would answer that question. And again, getting scientific notation typically means you write it out with the decimal point, and then you move the decimal point to where it belongs and count how many times you moved it, and that's your power of 10. Just I want to show you this. What if the number had been 0.75? What's that in scientific notation? Well, again, we need to move the decimal point so that we have one digit in front of the decimal point. We want 7.5, so we move it over once. And we know 0.75 is less than 1. So we're going to have a negative power of 10. So we moved it once. So that is 7.5 times 10 to the negative 1. And now I'm going to add something. If you watched this video before, it was incomplete because I got sidetracked and forgot to finish the calculation. So what we had done was we had basically converted 750 times 10 to the 2, but we hadn't completed multiplying that out. So let me just start again. It's whoa, what the heck? Okay. 750 milliliters times 10 to the 6th cells per milliliters. And if you've looked at the slides, you've seen the answer, but this is how we get to the answer. So again, I'll convert this to scientific notation. And I'll convert this to scientific notation. So this, we move the decimal point twice, and it's above 1, so it's a positive power of 10. So it's 7.50 times 10 to the 2nd power milliliters times 1 times 10 to the 6th. This just says 10 to the 6th, so we assume 1 times 10 to the 6th. You can multiply any number by 1 and it won't change. So 1 times 10 to the 6th cells per milliliter. Just like you can multiply by 1, you can also divide by 1 and nothing changes. So if you have a lone number like this, it's perfectly fine to divide it by 1. And what that allows us to do is see that this is on top, and what's on top cancels against what's on the bottom. So cancel milliliters, and we end up with cells. So now we have, let's see. So we're going to multiply 7.5 times 1. We're just going to start with these, and then we're going to do the exponents. 7.5 times, or 7.50 times 1 equals 7.50. So that's going to be at the start of our answer. And then what power of 10? So here we have 10 to the 2 times 10 to the 6th. So I'm multiplying this power of 10 and this power of 10. And when you multiply exponents, when you multiply these together, you add the exponents. So that equals 10 to the 8th. And there's a way of checking this if you're not inclined to believe my math, where we add up the zeros. So 10 to the 2nd power is 100. 10 to the 6th power is 1 million. We can add little commas. That helps sometimes. And so if we add up the zeros, because we multiply these together, we just add the zeros. 1, 2, 3, 4, 5, 6, 7, 8. So that's what that is. So 7.50 times 10 to the 8th cells this is our answer, and I can improve it a little bit. I can make it a little more specific. So what I could do is, whoops, yikes, I could change the units. I could change this to 750 milliliters per bottle. So that makes 7 milliliters per bottle. So our final units are cells per bottle. Per bottle. The final answer. And so in English, that's, what is that? 7.5 times 10 to the 8th. That's 750 million cells could be hiding in my little water bottle. And the water would still be optically clear. There'd be no evidence of cloudiness or turbidity. There'd be nothing you could see visually that would tell you the difference between that and pure sterile water. That's a interesting thing to know, and that can help you, like, if you're hiking in the woods and you see a crystal clear mountain stream, that the fact that it's crystal clear invites you to drink that cool, clear water, but it could very well be contaminated with bacteria or protists like Giardia. So don't ever drink water that hasn't been purified, either by a water treatment plant or your own purification stuff. And that's what we do in biology. So now I'm going to demonstrate peptidoglycan and a cell membrane. So remember, a bacterial cell is under pressure. It's got salt water inside it, and the world is hypotonic to it, so water is going to tend to move in, and the pressure is going to tend to increase. And that cell membrane is waterproof, but weak. And the cell wall is not waterproof, but it's strong. So I will attempt to show you what that looks like. So I have a balloon. This is a cheap balloon I bought for a project, and it will probably just randomly pop. But I think I can inflate it. If I kept blowing into this, it would eventually pop. It would explode. And it would keep getting bigger and bigger and bigger. Glorious. Now I have a sock. This is a sock. And if I blow into the sock, nothing happens. It doesn't hold air. So this would be like our cell membrane that holds air or water, but is not strong. And this would be like our cell wall that does not hold water or air. But I can't pop a sock. So I'm going to put the balloon inside the sock. And let's just see what happens. I'm like blowing as hard as I can, and I couldn't make it any bigger. And that's exactly the situation you find inside a bacterial cell. Sorry, I was blowing into that balloon as hard as I could. I turned red, but I couldn't make it any bigger than like this because of the sock. And that is exactly how bacteria keep their shape. The peptidoglycan has that bacillus shape, for example. The cell membrane expands out to fill it because of that osmotic pressure. Okay, that was lecture 2. Good luck, everybody. I will see you next week.